It's our great pleasure to have Dr. Mei Chen, Associate Professor from State University of New York in Albany, to give us a talk. Dr. Mei Chen is currently an Associate Professor in SUNY Albany, and from 2011 to 2014, she built and led the Intel Science and Technology Center on Embedded Computing at CMU. And she drove collaborations across four research teams involving 7 universities. And previously, she held researcher and research lead positions in Intel Labs, HP Labs, and SRS NAF Corporation. Dr. Chen's work in computer vision and biometrics. Dr. just mentioned is already enough. And I would want to highlight one thing, that is, in the previous about 10 years, she had already been nominated for 6 Best Paper Award. And finally, three of them finally got the Best Paper Award. And that is already pretty amazing. And her undergraduate and master studies in Tsinghua University in China. Now let's welcome Dr. Chen to give us a talk.
Thank you so much for having me here. I already have met a lot of faculty and students and really enjoyed the visit. Thank you for being so gracious and for the hospitality. And actually, I didn't get to sleep much last night and drank too much coffee, so I'm feeling a little jittery. If I talk too fast, do let me know so I slow down, because I tend to talk really fast when I'm a little over caffeinated. So actually, the project I want to talk about today is about a spatial temporal event detection. Rather than really like presenting some work, is more about a discussion and also more to show our experience of tackling this problem, more from a model-based approach or from a data-driven approach, and our reflection on the pros and cons, what is doing better, what is still left to be done. So here is a little bit of the outline of the work. Of the talk, and first I will talk about our model-based approach, and then the data-driven approach, and some discussions and the future work. So this problem is actually motivated by stem cell manufacturing. As you may know that there are not a lot of adult stem cells, and we need a lot more for doing research and also in the future deliver treatment. So typically, the way when they do stem cell manufacturing, they do this so-called subculturing process. And here, actually, they take first a number of sample cultures, and they try different conditions and see if the cells are behaving the way they would like. And when the cells are doing the way human like, at least that's how it's currently done, people kind of just eyeball it. And one is doing the way people like, and then they try to replicate the condition to a larger sample set so as to produce or manufacture more stem cells. And for this particular project, we want to have a computer vision system to hopefully automate this process and also make it more consistent in that way. And I will discuss this. And in particular here, one thing to pay attention to is that here is not sufficient to just count the number of cells. There is a strong interest and motivation in knowing the individual behavior of each cell. And actually there is already this kind of what they call laser tracer available. Ideally, they want to be able to manipulate individual cells, pick the good ones and let it do more, or pick out the ones that's not behaving well. And so this is the motivation of the project. The input to the computer vision system typically looks like this. It looks like a video. It's actually a time-lapse image sequence. In this particular case, the images were taken every 5 minutes, but it could vary, depends on the experiment. And also this particular imaging modality is a phase contrast microscopy, what you are seeing a bunch of mouse muscle stem cells kind of moving around in the petri dish. And the video is not video, the sequence is looping. You probably notice that it's getting denser and denser. So here is, of course, I'm probably preaching to the choir the more existing current ways of how biologists or tissue engineer researchers do their research. Because it's a really dense population, they typically take a region of interest, and then here actually what human can do is only to count the number of cells, and that's already pretty labor intensive. This is an example of what the researchers would publish in their work. The horizontal axis is time, so in this case the experiment is up to 200 hours, so that's also typically how long it takes, several days. And the vertical axis is the density. So you count the number of cells, see how much is how the density is changing, and use that as some kind of a quantitative measurement of what's the stem cell population is doing. Whether it's behaving the way you would hope to be. And as you can imagine, this from in terms of quantity and the quality, the information is not sufficient, right, for when we want to be able to engineer individual stem cells, like what we talked about in the previous slide. So then, what do we want as the output of the computer vision analysis? This is one example of that. Basically the process result of the sequence you saw earlier. Here, the different colors denote different identity of the cells, and the little tail is dragging is the recent trajectory of the cell. So as you can imagine, because I think it's mostly imaging people here, so the task here we need to do is that we need to do detection, tracking, and also in addition, different from say people tracking, is that cells can divide. They can actually also merge, and they may die, and they may differentiate. So there are many different kind of events or behaviors that we need to observe here. So the one I want to use as an example to discuss today is it's supposed to play. Sorry. This was playing earlier. Okay, now it's playing. So the event for behavior I want to discuss today is what's called mitosis. In more language I can understand, it's a cell division. The reason we think it's a very critical and important event is that here in this visual, the vertical axis is time. So you are seeing this image time-lapse sequence, right, going through time. And here we use several cells as an example. You see when the cell is dividing is when the trajectory branches, right? So in order to remember to get a result, we wanted to detect the cells and keep track of the identity and also keep track of the trajectory. Knowing if and when the cell divides is very important, right? Whether it's dividing and also what time frame. So that's why this is an important event to detect to obtain the final result we want. So this mitosis is actually what we call spatiotemporal event. Here, of course, is more of a perfect example. In reality, they don't all look like this. So at the top is more of an illustration. For these type of cells, when it's just on its own, not doing anything, it tends to stretch out. And in this particular phase contrast microscopy imaging modality, it also tends to have a halo on the side of it. And when it's about to divide, it tends to fall up, become rounder. And also because of the effect of this imaging modality, it will appear brighter. And then rounder and brighter, and then it starts to divide into two. And also this is what we call the figure 8 or birth event moment, where it's divided into two cells but still touching, and then gradually divided into two. So that's more of a kind of an illustration, a perfect example, right, of what that looks like. It's a sequence event, and this is we call that a birth event or time of birth when the cell divides. So the task for this mitosis event detection is to know if there is mitosis happening and also when, right? Remember, we want to know when because we want to know when the trajectory is branching, right? That's important. And this part is difficult, so we didn't really try the pure looking for figure 8. I think we know from past experience it wouldn't work, but here you can kind of more visually see the challenge of it. These are the horizontal axis is time. These are 3 sample subsequence of the data, and some of these are mitosis, some are not. I don't know if you can guess which ones are cell division, which are not really, because sometimes there's just 2 cells getting close to each other. Yeah, you can take a guess, and here is the result. So these 2 are actually real cell division happening. These one are actually just neighboring cells. So that's why you can see part of the challenge, and also part of the reason just processing that frame by frame may not be sufficient. It's useful to treat it more as a both spatial and temporal event. So in the so-called model-based approach, the way we were trying to that, at least the sequence of processing is quite typical, in the sense that we first detect some candidates and then try to incorporate temporal information, extract features, and validate the candidates. And I will show what it means by this process. So here at the top is just using a region of the input time-lapse sequence. In that sequence, we first look for, this is the very first approach, we look for so-called candidate regions. And these, remember I said, when it's about to divide, it starts to get rounder and brighter, and that's the kind of information we were using, and we were looking for patches that with the rounder and brighter blobs. That's of course not very sophisticated, but we will evolve. And then we change the overlapping candidate regions over time to form candidate sequence. And after that, for the visual feature computation, at the time we tried several different ones, and eventually went with a histogram of oriented gradients. So it's just a typical established image feature. All of these, the processing so far is pretty generic. There's nothing really novel there. What we contributed, or more, my collaborating student contributed, is this classifier to determine whether there is cell division happening, and if so, at which frame. And I will talk more about that. To determine 2 things in one step, if it's happening and when. So here is just very briefly what I mean. Here's the non-mitotic cell. It's kind of dark with a halo, and it starts to get brighter and when the birth event happens. And these are the kind of candidate patches it typically extracts. That's bright and rounded, and then that's how it's changed over time. Of course, there is some redundant detection or some overlapping, but remember, we are going to validate that during the classification step, and these are the features we extracted. Like what I said, there's nothing really fancy here. It's just using the hog feature, and also we did rotate the data to produce to achieve a rotation invariance to an extent, because the axis of these figure 8 could be different orientations. Those are pretty generic steps. Here is the contribution of this work. So before we did this, there was an existing work of using hidden conditional random field to detect if there is a cell division. So in that work, it cannot determine when it happened, but it can determine if there is one. So here is the input image sequence, and then the final label Y is either 0 or 1. Right? If there's a mitosis, is 1, otherwise it's 0. And another work that we learned from is work on latent dynamic conditional random field. Here in this case, for each input patch, it produces a label in the output. So we learned from these two pieces of work and came up with this. We are not very good at naming, so we just named that event detection conditional random field. Here you can see that that's the input sequence, and what's different from before is that we still have a final one label, but here we added so-called sub-label layer. What it does is that if there is no cell division, no event, nothing happening, Y is still 0, the same as the prior work. And in that case, the sub-label S don't really do anything. Just give them something just the same for everyone. For example, N. And if there is cell division happening, Y in this case is not 1. Instead, it's the index of where the birth event happens. And the S, the sub-label, will denote when the birth event happens and switch label right from B to A. So here is showing that in this case, there is no cell division, and the sub-label S is just the same. It doesn't really do anything, and the Y is 0, the final label. In this case, when there is cell division, this sub-label switches when the division happens. And by that also denotes the index of the frame when it happens. So in that case, Y is non-zero, and also the number is the index of the frame where the birth event happens. So here shows that again the input sequence, and when there's no cell division, the output label Y is 0 and the sub-label is the same. Here is that when there is cell division, the sub-label switches when the birth event is happening, and also the output label is the index of when that happens. So that's the design of this so-called EDCRF. And again, just to emphasize here, what we want to do is that given these test sequences, we want to determine if there is cell division, and also if so, when it happened, right? Two things decided at the same time. So here are the data sets we use for evaluation, and that's also what I was showing earlier, where we are already pretty lucky to have biologists working with us, and sometimes generating data on demand. However, still, this is the kind of the level of quantity we have, right? We have several sequences, and typically frames in the thousands and events in the hundreds. So that's the kind of scale of data set we have. And here, all the birth events were manually annotated by our collaborating biologists. Here is the just a qualitative evaluation of the result first. The yellow shows the automated detection result. Red shows the ground truth of human annotation. You can see that mostly it's doing well, but there are still some false positive and false negative. And often there are times the timing seems to be a little off. The yellow and the red don't appear at the same time. So that's it's doing okay, but there are some errors, and here we will show quantitative evaluation of the result. Here, the precision recall F measure is the standard. Here is what it means, right? So these are the two different kind of cells, right, that we showed earlier. What we mean here is actually like what we saw earlier. Sometimes the red and the yellow seem to be a little off, meaning that the timing, which frame birth event happened, the detection can be a little off. One frame means that here we allow no more than one frame, error. Here is we allow no more than 3 frames. So this is of course much more relaxed and lenient. And the result is kind of makes sense in that when the error tolerance is high, all the precision recall and F measure is higher, and when it's more strict, only allow 1 frame error is lower. And this number, go ahead.
Is that timing critical? I mean, in this case, 3 frames is probably not a big deal, is it?
3 frames may not be a big deal. I will show it when it's we also tried 5 frames, but then it starts to 3 frames is not a huge deal in this case. Also, and 1 frame of course is ideal, right? But it doesn't always achieve there. And also, what I mentioned is that the numbers really don't look impressive by today's standard. At the time, several years ago, it was better than the prior work. So at that time, we were pretty happy. But then I will show you when it starts to not working. Oh, here just to mention that sometimes we do penalize if there's a multiple detection of the same event, not just counting the right one, but also discount the other ones. And here is showing the localization precision, like what you mentioned. Here are the 2 different cell types, and you can see that for this one, it seems a little easier. So mostly it's actually doing really well within 1 frame error, with some more spread out errors. This one is actually a little challenging for our method. Overall, it's at least the distribution makes sense. And we did compare with this prior work that we learned from. As what I said, this one only decides if there's cell division. It doesn't decide when it happens. So what we did, arguable, is that we added, you try both using SVM or using another CRF to post-process this result and decide when the birth event happened. And then compare that result with our approach, where it's deciding 2 things in one step. So here is just a little just looking at the curve comparison. On the top is 1 cell type, this bottom is the different one, and the 3 figures are allowing 1 frame difference, 3 frame difference, and 5 frames difference. Here the blue curve is the PR curve of our approach, and the red and the green are the ones using a prior approach, adding post processing of using SVM or CRF. And here, we think when the threshold is more strict, allowing only 1 frame difference, we seem to show the advantage more obviously, significantly outperform the other approach. When we are allowing up to 5 frames difference, we still do better, but not as the advantage is not as obvious. So overall, we feel that having more strict criteria is probably makes more sense, and in that case, this approach does seem to have advantage. So this one was actually quite nice work by a student, and his very first paper got accepted at IEEE Transactions Medical Imaging. So we were pretty happy about it. until, so that's the nice thing about having domain experts to collaborate with you, until our biologists created a new sequence for us. So this is what they call a so-called high cell confluence scenario. This one was actually created kind of artificially. They first culture these cells in the petri dish until it already covers the dish. And then they artificially scratch a wound. And then they want to see how the cells, kind of grow back together. They call that a wound healing assay. So on this sequence, our approach that we were pretty, happy about performed pretty badly. So then we had to think about ways to improve, to do better. This was also, before the popularity of a data-driven approach. So we still continued the kind of thinking of model-driven approach and a similar process, but different specific approach. Here, the analysis pipeline, some people may cringe. So with the input sequence, the candidate detection is actually to look for the birth event. And for that detection, we use a extremely handcrafted feature. So it's the kind of extreme opposite of a pure data-driven approach. But at the time, we tried many different things, and this was the one that was giving us a reasonable result. So we actually defined this particular model for what it looks like when the birth event happens, and look for that and determine that as the candidate. And after we found these birth event candidates, remember before when we were looking for candidates, they were just bright round regions. Here is a much more specific, looking for something that looks just like that. And after we found those candidates, again we formed this temporal sequence as candidates, tracking few frames before, few frames after. And once we have this candidate sequence, again we do a validation, and I will talk more about this, how the rationale behind that. Once we validate, whether there is a mitosis or not, also that's when we can determine if there is a birth event or not. So in this case, I'm not sure if that's really considered a contribution, but that's what actually made it work for this very crowded cell sequence. Here, the very handcraft feature includes these two daughter cells, and also kind of modeling the contact region and the halo between them. It's pretty specific. We did allow some variation, so this model can. It doesn't matter if the cells appear dark or different intensity. Also, you can model that of different orientation. We did do that, but still it's a pretty specific model, and that's the birth event model. And here is the second contribution is this statistical model to validate whether the birth event is true or not. Here, again, we are not very good at naming, so our student named that two-labeled hidden conditional random field. So what does that mean? Here is the input sequence. Here, remember when we construct this candidate sequence, we actually first detected this candidate for birth event, right? We detected the candidate for birth event, and a few frames before, a few frames after, formed the candidate sequence. And then after this sequence, here in the sub-label layer, we only have two labels. basically one is before the birth event, one is after. And then the final output, label Y, here also takes just 0 and 1. If there's no mitosis, it's 0. If there's mitosis, it takes 1. So here, I think the best way to explain this is that here, actually what we are validating is whether this birth event is true or not. Before, we were trying to determine if there is mitosis happening, and if so, where the birth event happens. Here, instead, because the frame is so crowded and we couldn't reliably find the candidates well as before, so we actually designed this very specific kind of template to look for the birth events. However, the candidates we find, some may be true, some may be not. So this is actually trying to determine if this birth event is true or not. If it's true, then Y gets 1, right? And then we know there is mitosis and we know where the birth event happened because that is already our candidate, and that's also how we constructed the sequence. And if the birth event is false, then Y gets 0, and there's no birth event happening, and also no need to determine when it happens. So this is the rationale behind defining this statistical model. This is to compare with the previous approach. Again, here is deciding, is there an event, and if so, where is it? So here, the label Y is either 0, where there's nothing, or some number P, where the P is the index of the patch, right, that contains the event. Here, this U model, what's different is that we already first look for this candidate of birth event. And here, all what we're deciding is binary, right? Is this candidate a birth event? If so, Y gets label 1. And also we know now that that's how we constructed the birth event. This is a birth event, and the birth event is at this index. And if it's false, then Y gets 0. There's nothing happening. So that's it's a sounds similar, but actually quite a different kind of model from the previous one. So for this one, the data sets we use for evaluation is different from before. Here is the same type of cell, but more crowded than before. And also here is 4 different sequences using this so-called wound healing assay. So you grow cells to cover the petri dish and then artificially scratch a wound. And here is just 4 different sequences under 4 different kind of cultural conditions. The biologists wanted to study how the different cultural conditions affect how fast the cells, the wound is healing, how fast the cells grow back. Here is again, first just a visually qualitative evaluation of the performance. Yellow again is the automated detection result. Red is the ground truth done by our collaborating biologists. There are still occasional errors. Overall, it's doing pretty good actually given the data. So here is the quantitative evaluation, precision recall, and I've mentioned also area and the curve. So here are the 5 different kind of data. That's the average. So those numbers look pretty good. So these actually perform. It's how should I say? You can argue that it's a little rigid, not easily to generalize to different cell types or different events, but it did work well for these pretty challenging data. And also this is compared with the previous approach. This is the new approach, and I've mentioned the area and the curve, and this is the previous approach. You can see that's why we kind of panicked a little bit when we got this data. The previous approach really failed rather miserably when the population is so dense. And the new approach is handcrafted, but it does do better. So we also compare that against human, and that's an interesting observation. These are 4 human, one is a biologist, 2 are students, 1 is a postdoc. So, and this is comparing their performance in precision and the recall. Here is the average. So even for human, the precision is higher than recall, which is probably understandable that I think while a human determining that cell division is typically true, but sometimes with such a busy frame, they may miss some. And here is the performance of our approach. Is certainly not yet as good as human, but you can see that actually in terms of recall, it's getting close. So that's actually one idea our collaborating biologists had. They thought, maybe your system, although not accurate, not really useful, but maybe good to, since you have pretty good recall, to help us catch the ones we may miss. So that is probably one interesting direction to explore for at least getting better ground truth. And after this work, there were some improvements here and there, but nothing significant. We kind of doing different things and didn't do a whole lot. And then of course the data-driven approach was getting a lot of popularity. I was actually guilty of not encouraging data-driven approach on this project because somehow I was too conservative. I felt we didn't have enough data for training, and how can you really do deep learning on this? But then it's very good that our students insisted. So he said, well, let me just try how it will work. So here the approach itself is I won't call it really novel. Here we use the convolution neural network to directly learn the image features rather than either use HOG or use this really handcrafted one. And then here also we were encouraged by the success of LSTM on video analysis. So we employ LSTM to help us encode the temporal dynamics. Remember the cell division is a spatial temporal event, right? It's a sequence. So we tried these. This one, I think people may argue, what did you confuse? So here we the input actually instead of really detect these candidate patches like what I said in looking for bright round blobs. Here we more use just a spatial sliding window quickly and did a background subtraction to remove the background. And then here we used CNN architecture very similar to LeNet and to extract the image feature. And then here the output of that to LSTM for sequence learning. And then a final fully connected layer to produce labels for each input frame. So this part, that's also what I have to be very impressed with. What we did was really pretty generic, right? How people would typically approach is using CNN, LSTM. Here the analysis pipelines are similar. And here is the result. Even though we use something just really quite generic, and the performance is quite amazing, I have to admit. And we did try using CNN only learn the image feature without LSTM. And then here, only using LSTM, still, use our hub feature, something like that. And it's probably not too surprising that, using CNN in addition to LSTM gave us the best results. And we did compare these to other approaches. Here is our, the event detection conditional random field, the one I talked about first. And by now, when you look at the performance numbers, it's pretty sad, right? Several years ago, it was still the best. And then here is something in the middle, another researcher explored. This one is a hierarchical CNN. So what's interesting is that in this one, in order to encode the temporal dynamics, they used a hierarchy of CNN, used 13 of that, and also got pretty good results. And at the top is our approach. And here, it's like your point. When the error margin is really, we only allow really small, like 1 frame difference, we seem to do best. If it's really relaxed, like 5 frames, actually these HCN does better. So our approach probably overall does better, slightly, but when with this HCN, the performance is already very good. Here, I guess what we could argue the advantage of using CN plus LSTM, versus using 13 convolutional neural networks is that it's a more efficient way. Have many fewer parameters to train, and also for data augmentation, we did do data augmentation to make it work using because we didn't have additional data. And for that, we only need to do rotation, 90 degrees, and 90 degree, 180 and 270, and also did mirror reflection, but that's all. With HCN, they did have to do many more data augmentation to make it work. So that's some comparison there. That's with one cell type, C3 H type. And with these other cell types, this work didn't report results on that, so we compared with the very original approach. And of course, I had to be impressed that using CNN plus LSTM, it's significantly better, more than 10%. So that's a quite impressive result. Here is just a qualitative evaluation. Here, I think our student used blue to show true positives, so the blue ones are the correct ones, and the red and yellow to show either false positive or false negative. So overall, it's doing pretty well, and there are still some errors. And this one, I should also mention that this sequence is pretty challenging, but still not as challenging as the wound healing one that we mentioned earlier. And this approach cannot handle it when it's that crowded, that high confluence. So there's it's pretty impressive, but it's not. Even though the previous hand-practice feature was really not elegant at all, it still is the only approach that can handle that data. So that was work done in 2015 and 16, published in 2017, and then our students are always the fastest at adopting the new approaches. So then we started trying this attention mechanism. This is a very preliminary work. It's not yet published, so the jury is still out whether it makes sense or not. So here we used, again, with the input sequence, here again using sliding window. And first use CNN to learn the image feature, and using LSTM to encode the spatial dynamics. And here is what we learned, of course, from the popular work using this soft attention mechanism, and then use the LSTM decoder, and finally get the label of the sequence after the fully connected layer. So here is just some, we are still working on it. Here is just some intuition that seems to make sense and promising. Sorry, I was lazy to change all the colors, so sorry, the background is a little different. Here is just to, a little bit visual intuition to show, what it means by this, attention mechanism, how, how it's different on positive or negative sequences. So the top two subsequences are so-called positive sequences, meaning that they contain cell division, and the bottom two are negative sequences, meaning there are no cell division. And here, the numbers show this, attention, so-called attention number. So at least, from this visual intuitions that it does get, a higher attention number when there is cell division happening in this positive example. And also it does happen when, the cell is starting to divide. And the intuition for these two negative examples is that since there's no cell division, right, the attention is, it doesn't, all of a sudden increase when there's division happening. And the decision is not made until the last frame. So essentially the last frame is actually what determines all the way till the end, okay, there's no cell division. Just some intuitive sense of why the attention numbers looks like this, and probably makes sense. So here is the current performance comparison on 4 sequences. In this study, because we felt really not having enough data is hampering progress. So we actually do have more raw data. We just don't have more. Our previous collaborating biologists who went on to their own faculty jobs, so we don't have people to help us label. So what we did was that we have you can argue we have our own students label that and have our biologists double check. Right? So to hopefully get more label data quickly. And here is to show the performance comparison with the previous approach, and in particular, I guess what worth noting is the blue. Compare the blue color and the gray color. The blue is the latest approach, CNN plus LSTM with the attention mechanism, and the gray bar shows the one I just talked about earlier, just CNN plus LSTM. That's a precision recall and F measure. And you can see that for precision, we are pretty consistently doing better than previous approaches. For recall, it's actually not better, it's worse. And that's something we are still analyzing. Is it because we are too stringent on this? F measure overall is doing better, I guess thanks to the higher precision, with the exception of this particular sequence. So these are different sequences we annotated under different cultural conditions that biologists use. This is, like I said, we're still working on it and deciding whether this indeed has an advantage. And also, what we want to do more is that so far we still, using data-driven approach, using deep learning, CNN, LSTM, has given us really amazing performance on typical data, but not the really high confidence data. But we want to be able to handle that, right? So we don't have to have this a little bit, too handcrafted approach. What we intuitively we hope using fine-tuning may help us, tackle this higher confidence data better. And also, we are still debating about this. Maybe doing some pixel level segmentation will help, because currently the reason is that when the cells get really crowded, and when you try to find candidates, there's too much overlap between that, and so that causes errors. Maybe pixel level will help, and also since before we had some success with using graphical model, we thought maybe we could also leverage that together with deep learning to get better results. But that's still definitely needs further investigation, and of course working on other events as well. Because I do want to mention this is a challenging slide for this computer. Let's see if everything can play. So I only got to talk about mitosis detection, the cell division detection, but actually, I think the computer doesn't like it. I think it's probably demanding too much of the. But basically, going from this input time-lapse sequence to this output with different identity and the trajectory, there are actually multiple events for behavior we need to be able to detect. One is migration tracking. That one actually we so far got decent results using global optimization with a frame-to-frame association. It's not a sophisticated approach, but so far there is actually nothing that does better than there could be a lot of interesting research done. And that's mitosis. That's also apoptosis is cell death detection. That's actually a very challenging task. We touched a little bit, also not enough. When the cell dies, it's also a process, but not as neat as a division. It could just stay the bright blob, and because when cell dies, it also gets brighter and rounder, and it could stay that way. It could explode or get dragged around by other cells. So it's not very neat. And of course, we chose the easier one to start with. This one could use more work. And the last one that is not playing. Differentiation actually only happens when the confluence is really high. We only touch this problem by treating that as a texture analysis. So there is no real consideration of the temporal dynamics, because it's so hard to really keep track of a very dense population. So there is definitely also opportunity for a lot of research there. And I should put a plug that all this data is open source. It's on the website, and definitely more than welcome to use it, because I think it's a very interesting and important field that could use more people contributing and doing better than us. So that's other things we could work on. And also, before I leave you with that, just to, because there are always people say, why do you keep working on this? It's such a specific, narrow project. Actually, it may have more applications than you realize. So this is some of you may recognize. This is actually the let's say the big religious ritual progression around Mecca in Saudi Arabia. So what you see is that these are the landmarks, and all these little dots are actually people. They all try to follow this progression around certain ritual and routine. So for the person who gave us this data was really kind of joking, because he saw the cell tracking result and he said, well, you put that, because we were bragging a little bit, we said, oh, this is large scale tracking problem, very challenging. And he said, what about this data? Can you keep track of these people? So we have no idea how what the ground truth will be like. So actually what we did was just applying the cell detection. Of course, no mitosis here, and people don't divide. We just applied the cell detection and tracking module to that. Didn't really modify it. And here are the results from 2 regions of interest in the previous slide. So each different color dot denotes different identity of the people. And here the little tail shows the recent trajectory. And when it ends, the ends shows the trajectory. And for each one, as you can imagine, we have no ground truth. there's no way to evaluate the accuracy of a detection or tracking. However, the person who gave us data was not really interested in knowing each identity of the person or their trajectory either. What the person is interested in is actually this kind of pattern, right? When the progression is supposed to be this way, and there are these individuals cutting it differently and could potentially cause dangerous events. So that's the thing they are interested in. So you never know. Cell checking may be also useful for crowd control, because here at this scale, the people also look at little dots over cells. So that was just for fun. We actually have no idea how accurate it is, but visually seeing the trajectory does correlate to these individuals that are cutting through the procession. So anyway, I'm running out of time. Just to wrap up, so for spatial-temporal event detection, is it good to take model-based approach or data-driven approach? We've tried both, as what I've discussed. Conclusion, I think, at least from my current understanding and perspective, I still feel it's necessary to incorporate any knowledge or insight we can use from the problem domain, and that could possibly help enhance the learning process. Just learning from pretty much raw data for very challenging data in our experience is still sufficient. But that could be because our data was not big enough. That could be part of the reason. So we are still exploring and reflecting and hoping to know better. So that's my current conclusion is that I feel that data-driven is important and very demonstrated very impressive performance. But I think some model, if we know, will also help and make the learning effective. So that's all for my talk.
Any question? Yeah.
Go ahead.
I was curious. I have 2 questions. First, just kind of out of curiosity, was it necessary to pre-train CNN writing, or could you train directly on the on your cell data, like the cell data that you had?
You mean for the CNN?
Yeah, for the CNN-based architecture. I'm curious.
So we did use a sliding window to look for these so-called candidates, and then we train on that. Yeah.
Okay. So it wasn't like pre-trained on some of the data sets without that. Okay.
Yeah.
My second question was, would you consider using like a semi-supervised approach to get better label efficiency? Like there's a lot of things like with reconstruction losses and stuff like that incorporated.
Yeah, that's definitely something we want to do, because I think that will make more sense. Yeah, because as you can see that our data is so limited. Sometimes I also worry if we are overfitting. So yeah, that's a good question, good suggestion.
Other question? Yep.
I was curious to know what the attention mechanism in the middle of one of your slides. How did you implement that? Which one did you find was?
So that one we actually just followed paper. Yeah. So that's why I must admit that for this kind of work, I sometimes also frankly worry about publication, because people may question what is your contribution. Because for the architecture, we just use existing ones, follow, yeah. And so people could argue that, is it a novel application of existing architecture, or is there any contribution to the architecture here? It's interesting how you think about it, because I was also talking to the student the other day. On the one hand, he just used the most generic CNN and the LSTM, just from the paper, and but it gave us 98, 99% performance. So from that perspective, it's really impressive how well you can do. But on the other hand, there is also this crisis. Then what is your contribution? So that's why I'm pushing for more investigation on these more challenging data. When it's really high confidence, these still cannot handle it at all. And is there something more interesting we can do? That's also contribution to the architecture or the methodology itself, like not just a new application. Yeah. that currently, that's why I still kind of took your time to talk about that part of the work. It's not really elegant. I don't really like it. We kind of built this template for the birth event, but that's the only thing that worked for that data so far. Yeah.
Okay. And
Yeah, go ahead.
okay.
Are you training and testing on the same, like how are you?
Oh, no, we're definitely
separating?
separating. Yeah, definitely separating. That's also, why the limitation of data just really shows, because that's also why we, basically annotated ourselves, these sequence. People could argue that, how trustworthy is your own annotation, but without that, it's too limiting. Because we need to separate training data, and also we use a separate sequence for validating the, we call that sliding window approach to detect the candidates, and then we use another separate sequence for testing the overall cell division detection. So
But,
that,
but it's the same group of, data that you're using. It's not different, like a different setup of a microscope. It is the same sequence.
it typically is of the same microscope, because we collaborate with one group of biologists. They only had this one phase contrast microscope. Cells sometimes are different, because there's these C3H10, C2C12, and culture conditions definitely are different. So that part we can handle. So even if we use the same microscope and same cell, they put different chemicals, I think they call culture in it, and that typically causes a different behavior. Some make the cells divide a lot more. Some make them die, or things like that. So that part is definitely different. Cell type, some are different, some are same, but microscope is the same. Yeah.
Okay, we have reception outside. If you still have questions, you are welcome to ask the speaker and give period.